Hello, I'm Dr. David Kortowitz and welcome to Solidworks. Today we're going to be looking at motion analysis. This is how we can take our parts and assemblies and add motion and animation to them so we can see how they will work when they're finally constructed. Let's begin. For today's lesson, I have built this cam and piston setup. We have a cam at the top which has an offset driving this piston up and down. To analyze sort of how it's going to work at first, we can take this cam and start to rotate it. You can see the piston goes up and down with a little bit of oscillation in the XY direction. So what we're going to do here is we're going to attempt to add a motor and look at how our animation works. The first thing we need to do here is look at the bottom, and we can see that we have a tab that says Motion Study 1. By default, this will be present unless you have shut off the motion animation module, which is automatically loaded at start. If we go over here, we're going to get a series of timelines at the bottom of the screen, as well as some tabs up top. And the first one here says Animation. We can pull it down and we see that we have animation and basic motion. The problem with these two settings is that they ignore most of physics, and therefore if we attempt to sort of model how things really work, they're not going to be very realistic. To fix this, we can go to our Add-ins tab here in the ribbon, and we can turn on the Solidworks motion module. By doing this, we can now do computational simulations of motion. So we're going to set up our model and zoom in so that we can sort of see what's going on. And now, if we come down to this timeline, we have the ability to scroll down and choose motion analysis. When we choose motion analysis, it will automatically now compute using the general laws of physics. However, we have to set up these rules and laws, and we'll sort of be able to go through that on the next model. For this model, we simply want to apply a motor to the center of this cam. So basically the motor will turn the cam and the cam will move the piston. To add a motor, we're going to go down to our menu options, which are down right here above the timeline. And we're going to go across and we can see that we have this rectangular box with an arrow that's called motor. If we click on this, this will allow us to enter a motor of different types depending on exactly what we need. In this case, we have the choice between a rotary motor and a linear motor. In a linear motor, it shifts things in a straight line, where a rotary motor is what we kind of think of as a revolute type motor that spins. So the thing we need to do is determine where we want the motor. So we're going to designate where the shaft of the motor is going to be. And the shaft of the motor should be probably on this drawing in the middle here. So we need to pick an edge somewhere around the center point to place our motor. So if I click here on this edge, you're going to then see an arrow in the middle indicating the direction of motion. If we want to reverse this, we can simply hit the reverse direction button, and now our arrow goes the other way. Continuing down the screen, we have at the bottom our motion type, and right now it is set to constant speed. We can bring this down and we can look at distances, we can do oscillating, we do segments, we can do all sorts of things. But in this case, we want it to rotate, and we're going to stay at a constant speed. It is currently set to 100 revolutions per minute. This is relatively fast. For the purposes of this exercise, I am going to lower it to 10 RPM to make things a little more visible. We can go down and see that this is all set up and we seem good with this. So we're going to click the check mark here, and what you're going to notice is we now have our motor down here in our motion analysis timeline. In addition to that, putting the motor there, we now have a yellow bar coming from the motor going to what we would consider our endpoint. We also have up here our black diamond and to a black diamond, and this specifies the length of the video that we're going to be creating, or the length of the model we're going to be creating. To do this now, we can extend this or reduce it or do whatever it is we need to do. Once we have the model in a state we want, we can set up our starting view by zooming out and zooming to the position we think would work. If we agree with this now, this position, we can go down to our Calculate button, which is next to the drop-down menu that you selected Motion Analysis, to begin computing our model. So let's hit that button, and you'll notice that the thing starts turning. In this case, it only turned around 2 times, and if we run it again, you can see that it slowly turns around, and that's due to the speed that it's running at. Right now, it's in a jog mode because you can see that this here has a loop around. We can pull down that menu and we can go to playback mode normal, which will just play through once and then end. The sound there is telling you that you're at the end of your animation. We can extend the animation a little longer so we can see more things simply by grabbing this black diamond at the end and extending it out to where we want to end. So in this case, let's say 10 seconds. We now must recompute the positions of everything else by hitting the Calculate button. What it's going to do now is it's going to compute this for 10 seconds, and now we can go ahead and play our animation over those 10 seconds. And you can see the motion. Now let's say we wanted this to go a little faster. We can alter the speed of the motor simply by right-clicking on the motor itself and hitting Edit Feature. We can now increase it, say, to 50 RPM. It's roughly 1 rotation per second. It's a little less than that. And so now we have to hit the Compute button again to update our model. It looks like it's moving much, much faster there as it was computing. Let's go ahead and hit the Play button and see what happens. You can see that our model operates much, much faster. This is a good thing because it allows you to simulate exactly what's going to happen over a fixed period of time. We can also export this animation, should we want to, by hitting the Save Animation button. When you do this, it lets you save it as an AVI file, as a Flash video, MP4, or other format should you want to. You can also set the aspect ratios as well as the dimensions of the video and as well as the time that you want to do. So at this point, the entire animation is 7.5 frames with a total of 10 seconds. Should you want to go for longer or shorter, you can adjust that here or in the animation. Now this will give you the quality of video that we see here on the screen. This quality may not be exactly what you want. You may want something more like Photo View. To do this, we can simply turn on the Photo View 360 module and wait until we see Render Tools appear. Now if we go back to our Export Video, we're given an additional option. We can choose our renderer. And if we choose our renderer, the initial option is Solidworks Screen, but if we pull down, we can choose Photo View 360. Should we use Photo View 360, this will take much longer to go through saving the video. However, you will get a photorealistic version of your object operating. This can be really good for presentations and things like that that are trying to express what this will look like in the real world or in a real environment. Now, the use of motion to analyze how a piston system works or a motor system works is really useful for certain things. However, it really doesn't tell us much about how the natural world impacts our part. For that, I've built another model. To explore the use of real-world physics, I have created this model, which contains a Major League size and weight baseball and a green field below. We want to look at what can happen in the real world if we, say, drop this baseball to the ground. So if we go over to our motion study again, we have motion study 1, and we can choose animation, but we really want to choose motion analysis because we want to apply real world physics. So right now, since gravity isn't on and there are no forces on the baseball, the sum of the forces equals 0, so everything is going to stay still. If we want to start things working, we need to apply gravity. So to do this, we're going to go along our bar atop the timeline, and we're going to choose our gravity section. And now we need to look at the triad at the bottom to determine which direction gravity falls. In this case, if we notice, the y is upwards, so that means our negative y direction is going to be our gravitational force. Now, if we look on the right side of the screen, we have a little vector here, and this vector is the direction gravity is applied. So right now it's applied front to back. If I switch it to y, you can see that it is applied down. Now, on the command manager on the left, we have the ability to flip the direction of gravity should we need to make it fit the model. Now that we have it set at 9.80665 meters per second square, or 9,806.65 millimeters per second square, we can click OK, and we'll notice that we get a couple bars on our timeline. Now, in the real world, if we started the animation right now, we would expect our ball to fall to the surface and stay. If I run this, however, and run the calculation, you notice that the ball falls through the ground. And the reason this is because SolidWorks is attempting to save as much computational expense as possible to compute this as quickly as possible, so it ignores the contact between materials unless you explicitly state you don't want it to do that. Now, to change this, what we're going to do is go back to this menu atop the bar, and we're going to choose the one that says Contact. When we choose Contact, and my apologies, I clicked Gravity again, but if we choose Contact, we have the ability to sort of use solid bodies or curves. We're going to assume that we're using solid bodies. Now, one thing is, if you notice, because we are all the way at the end of our animation, our ball is missing. So I'm going to cancel this just for 1 second, and I'm going to scroll back to bring our ball back where it belongs. Let's go back again and hit the Contact button. And now we can choose which bodies we want to have recognize contact. So we want the ball and the field. Now, if you have a very complicated model, you can choose to use contact groups, which allows you to select the particular ones that you want to interact with each other, as opposed to what we're doing now, and we're just sort of saying gross, the two that are in there are going to interact. This will save some computational time, but in the end is less accurate. If we come down here, it allows us to select the material from a list. We have a few materials here. This sets up our impact parameters, our friction parameters, as well as our restitution coefficients. Now, if you want to do this a little more realistically, you can set these parameters manually by simply unchecking the little checkbox by material. But for the purposes of this demonstration, we're going to go ahead and say that the ball is made out of rubber and the ground is made out of, say, steel, dry steel. Now, if we manually set it, we may set things a little bit differently, but right now we're going to leave it the way it is. And we'll see what that impact is in a moment. So if I apply this and click the check mark, now we expect everything to work correctly. We now have gravity applied as well as our solid body contact. So let's go ahead and compute this again. And if we notice, the ball still falls through the ground. The reason this is because the ball is relatively small relative to the ground, and therefore, to save computational power, it's computing at a much lower complexity model. To fix this, we can go over to our little cogwheel here that is our motion study properties. Things that we want to do now is go ahead and use a relatively precise contact model, and we want to increase our accuracy. Now, and it's important to note that if we increase our accuracy too much, this model is going to become too complicated for SolidWorks to want to solve, and SolidWorks will then only solve part of the model. So let's try it here at most of the way to high, as well as a very high precision contact. So let's go ahead and try to do this computation. So I'm going to click the OK, and I'm going to hit compute. Now if you notice, it hits the ground and it bounces a couple times before it settles. If we change, say, the material of the ball, simply by going back into our solid body contact and hitting our edit feature, we can now say that instead of rubber, let's say that the ball is acrylic. If I click OK now, we can rerun our computation, and you're going to notice that it sort of lands on it and stops. That's a little more realistic for how a baseball might act. Now, what if we want to quantify this? Quantification is an important thing for most engineers. So we can quantify this using our plots. So we can choose this XY graph over here, and we have a bunch of different selections that we can make. So if we pull down, we have the choice of displacement, velocity, acceleration. We can look at forces. We can look at momentum, energy, power, and then we have other quantities, which gives us a whole bunch of other choices. In our case, let's look at displacement, velocity, and acceleration. So we're going to select that. We then get a subcategory. We can do trace path, which really isn't what we want, but we can do something like center of mass position. So that's going to give us the center of our ball. So if I click on that, and then we can pull down, we want the Y component because that's the direction of gravity. So let's go ahead and choose our Y component. And now the final thing we need to do is select which object. So we're going to choose the ball. If you notice, we now get that center of gravity logo, much like what you've seen before when you're doing free body diagrams and things like that in physics. So let's say OK, that's the graph we want. Now what happens is it's going to display a plot that contains the results of our study. So we can now move our plot bar and look at different times where we were. You also have the ability to export this as a comma separated values file, so you can load it in programs such as Excel or MATLAB. Let's go back and rechange our contact force to the rubber instead of it being acrylic again. So I'm going to go back to rubber dry, and I'm going to click OK. Let's recompute this. If you remember, it bounces up and down and up and down. And we're going to finish our computation, and then let's take a look at the graph. There's our graph, and you can see how much it bounces. So this height is being dropped from 1.2 meters, and you sort of see it bounce until it stops. We have additional options that we can use here to make the model give us more and more information, but right now this is the effective method of being able to see how something falls and how gravity and things like contacts and forces act on our model. So in a nutshell, between the motor setup and this gravitational and physics setup, you can pretty much model any type of motion you would like to in Solidworks. I would like to thank you for your time today, and see you next time.